Now, finally, I think is the time for string theory to enter. So how does it connect with the holographic principle as it relates to black holes and help make sense of entropy and this information paradox?
So string theory is a new idea that originated in the early 70s by thinking about the most elementary object not as particles but as little tiny vibrating strings. So they don't like point like, they're really a little extended, so they have a certain size. And even if you excite them, I mean, they're like really vibrating strings, and you can put more energy on a string by giving it excitations. So it vibrates and it can get a little larger. It's more like a little rubber band that also stretches a bit. And so the more energy you put in, the larger it becomes. And that's sort of similar to what happens, by the way, to black holes, where if you also put more mass inside a black hole, it also gets larger. Now, what happened in the mid-90s is that we discovered that string theory not only has these little strings, it also can have objects that not just one-dimensional, which strings are just one-dimensional vibrating objects, but maybe there are things that are more dimensional, even like 2 dimensions, when we would call them a membrane or something like that.
Brains.
And so this led to a new way of thinking about, well, objects in string theory that can be made together by putting these brains and strings in one object. And then you can imagine that there are many ways in which these strings and these brains can connect together. We're making more brains on top of each other, and then having more strings between those brains. And it's basically, that's the way that we eventually started to understand more what the microscopic language is to describe black holes. I mean, so we had a development where we could think about those membranes and strings put together as being actually equivalent to black holes in string theory. And then by counting the different ways of these strings and membranes together, we found a match actually between what the black hole area would be, the horizon area, and the amount of information that's associated to these micro states of these strings and membranes. So we made indeed the language, I mean, the map between the black hole area and the horizon area with the entropy, but then interpreted as counting the number of microstates or the microscopic possibilities of the microscopic theory. So string theory showed that it was capable of writing down the quantum mechanics of black holes in such a way that we could explain this entropy that Bekenstein and Hawking had calculated. This, by the way, was work that was done by 2 of my colleagues at Harvard, Andy Strominger, who I know was also on your podcast, and Kumran Wafa, and they together, and they gave a very beautiful explanation of the entropy of certain black holes with charge, I have to say. At that time, it was still in some larger dimension, 5 dimensions. They needed some extra dimensions for that. But eventually, we understood it in more cases. And also for these black holes in these special universes with this negative curvature, we could also give an explanation. So in string theory, we have ways of explaining the entropy of black holes by also making use of the fact that string theory is more than just particles. It's also more than just strings. It has many more things happening there. We call this degrees of freedom, in the sense that it's not just the matter that went into the black hole that is describing its entropy. It's really everything that happens, well, how should I say, is more microscopically in the language of these strings and these membranes. And by the way, if you think about then where these strings and membrane are situated, they indeed become kind of large. The fact that string theory has extended objects, and as I said, if you put more energy in the string, they become bigger. That same happens to these membranes, and they basically have the size of the black hole. So there's some way that the extended objects that string theory is describing is also mapping onto the extension of this size of this black hole. So this is where the match also comes from in explaining why there's more information in a black hole than just the matter that goes in.
This question is certainly not rigorous, but just how do you conceive of or visualize the core of a black hole? I mean, as a string theorist, you just sort of visualize a writhing ball of yarn and brains that is the composite of everything that was the star before it went supernova and that was subsequently sucked in by the hole. Is that just how you see that internal dense nugget?
So what I see is what I mentioned, that the matter that falls into the black hole eventually gets stuck. We don't see it ever disappearing behind the horizon. And Hawking showed us that temperature that the black hole radiates. So the temperature of this object also becomes larger. I mean, there's some way that's a hot object. So I think about a black hole as something where all the microscopic degrees of freedom are being excited and form something of that size. And I think about that as the brains and these strings sort of put together. So that some way this matter that was approaching the horizon and got stuck and got sort of mixed over the horizon area eventually gets put together in a tangle of brains and strings on the horizon. And that's how I think about a black hole. Of course, when I fall in, I will not be able to see all that stuff. I will just cross and fall into the horizon. And so what we're learning here is not just what black holes are made of, it's really what space-time itself is made of. So this is why studying black hole is such an exciting topic, because it's telling us not just about black holes, it's telling us about space, time, and the microscopics of it. Just like what we eventually learned for matter. I mean, matter, we eventually learned that it's made out of molecules and atoms and has fundamental building blocks. Now we're learning that space-time also has sort of fundamental building blocks, and those we can understand in this string theory language.
No, this is very interesting. So I understand that when we look at the black hole from the outside, we see the matter that went in sort of being imprinted there. But are you saying that you don't ever think about what the core of a black hole is like, because all of that information is on the outside and that's all you need to think about to describe it?
That is exactly the way I think about it. You don't go into the core of the black hole. Of course, as I said, when you fall into the black hole, you will be able to enter it. And then according to general relativity, what happens is that, you get feel a stronger gravitational force that eventually becomes infinite at the center where you have a singularity. But that's not something that you can see from the outside. And it's also not a useful way of thinking about the black hole from the outside, and not the physics of it. I mean, the falling into the black hole is basically that you get absorbed by this hot gas of all the strings and brains. And that is what happens to you.
Is part of the reason that you don't want to think about the singularity is that we know that our theories don't accurately describe it? So quantum mechanics and general relativity break down there. Is that part of the reason why it's just not worth thinking about?
Excellent question. So there was a time when we thought that the only problem with general relativity was the fact that it has singularities. And Roger Penrose, who worked also with Hawking on theorems proving that black holes have singularities. Those are the singularity theorem. And he earned a Nobel Prize for that. But he also had another observation, which he couldn't prove, but so it became a conjecture, namely that every singularity inside a black hole is basically invisible. There's a horizon around it so that we cannot see it. He called this cosmic censorship. And so I think that's a fundamental idea, namely that from our outside, the horizon is the end of space-time. It's not the singularity. It's from the outside, we don't see beyond the horizon. And in order to describe what's going on, we don't need to go all the way to the horizon. We have to go first to the singularity. We have to go to the horizon. So I think that this is actually what Hooft was telling us already in the early 80s, that indeed the answers to the questions about black holes were not by understanding the singularity, but by understanding the horizon. And at that time, it seemed very weird because most people thought about the horizon as a very normal part of space-time. But nowadays, we understand that there is a way of thinking about the horizon as really where all this quantum physics is happening, and also where you mentioned black holes as chaotic and object. Actually, this is also why we think about horizons now, is that a lot of things are going on there that make them into something with very high entropy, but also with a lot of chaotic things happening in at the microscopic level. So horizons are not as simple and nice objects that Einstein's theory would have told us, but they're really very complicated and chaotic places of space-time.
Before we move on to entropic gravity, I have a couple of broader questions about what we've just been discussing. And you mentioned Strominger and Waffe, Strominger, whom I spoke with recently, and how they solved this major 25-year-old problem in cosmology of Bekenstein-Hawking radiation using string theory. And this problem for 25 years evaded solution by more conventional means like quantum field theory. And on the one hand, this seems like a super strong indication, not that there aren't others, but taken in isolation, that string theory is correct. But it's also still conceivably not correct, as evidenced by many of the people who don't think string theory is the right theory of quantum gravity. But what I'm wondering is how it could have been so successful for solving problems like this, but still be wrong. What are some of the possible scenarios? How might you explain string theory's immense effectiveness in physics if it is still wrong?
Well, this was actually an insight that I had already some time ago, is that even... No, well, I have to answer this question in several steps. First of all, I agree with you that what string theory did was amazing. I mean, it's a breakthrough. And it also told us that string theory has the right elements to explain these. So string theory, there are various ways of sort of thinking about what is string theory. People have written down a formulation of string theory that has 10 dimensions. It has supersymmetry in it. It has a very specific way of having to compactify. I mean, taking those extra dimensions and roll them up and make them tiny so that we get our 4-dimensional or 3 space and 1 time dimension out of that. And that part, I think, may not be exactly correct, but that is not necessarily telling us that it's wrong. I mean, at least there may be other ways of using string theory, or maybe extending it or using its principles, so that we eventually get to the right theory. So I always think that string theory has the right elements, but it may not be the final description. I mean, the description we have now may not be the final one. And there's ways of explaining this a little more in detail. I mean, there's now we have a very beautiful, actually the most successful theory of elementary particles and the fundamental forces is the Standard Model. That is indeed described in quantum field theory. But there are many quantum field theories. I mean, quantum field theory is a framework which can have many realizations. So the Standard Model is one particular one where we write down a particular set of particles. We have a particular set of forces, but it's not say, the most symmetric one. For instance, there's no supersymmetry in the standard model. We could have written down a supersymmetric model. We could have even written down a model that has so much supersymmetry that all the calculations that we would do in the standard model would be finite without ever sort of having to do all the tricks that we now have to apply, the ones that Hooft invented. So, I mean, that Hooft basically showed us how to remove infinities, for instance, from our calculations. But there is a very beautiful formulation which has supersymmetry, but it's not our world. And so string theory can have the same problem, that we have added so much symmetry to it in its current form that it may not be our world. So one of the ways we have to sort of extend it is to think about more general formulations of string theory, which has fewer symmetries and maybe, maybe kind of a little bit of a different theory than what we are thinking it's now. But its principles are correct in the same way that it's sort of, I think about it also as a framework that has many more realizations. And so what I have learned from string theory is indeed the way to think about the microscopic description of black holes, for instance, but also more generally about how to think about these molecules of space-time. And I think the lessons we've learned from string theory should be taken seriously. This is where I think my approach indeed sort of differs from what Hooft nowadays is also still thinking about, and maybe other people that think about quantum gravity. But if you're ignoring what's going on in string theory and what we have learned from it, you're probably ignoring a very important lesson that we should incorporate in our final description of what quantum gravity is. But whether that is string theory, yes or no, we don't know. And maybe it's good to mention that now, right at this moment, we are having meetings. One is happening in Santa Barbara, which is about the question, what is string theory? And so many people working in string theory have not fully agreed yet about what is string theory. So we have not found the final formulation. So I think most people, and certainly the younger people that have entered this field, would probably agree that the formulation that people took, say, in the 70s and early 80s of string theory may not be the final one, and that we need more ingredients or have to combine it with our current understanding of black holes. Because certainly in the last decade, I think the whole emphasis of our research has not been so much on string theory, but more on thinking about the question of black holes and their entropy.
Just to reiterate and make sure that I'm on the same page. So when you say that the success of string theory in solving problems like Bekenstein-Hawking radiation, it suggests that strings, brains, these are here to stay, the principles, but which Calabi-Yau shapes correspond to the extra dimensions, what symmetries there are, the relations between like the various string theories like heterotic E and O and so on. These things still, there's room for development, and we don't have the final theory yet. But you think that point particles, for instance, are gone and strings have replaced them, strings and brains.
Yes and no. I mean, one way I would formulate it is that maybe by thinking about black holes, we're also thinking about different principles, and that we're going to eventually connect them to what we will learn from string theory. I mean, there's some way I believe that we can even eventually derive something like string theory from other principles. So the idea that string theory has to start from the assumption that you replace particles by strings, that already assumes that we know what a particle is or what a string is, and that's assuming something about space and time. So the thing we have learned now in string theory is that we first have to ask the question, what is space and time itself made of, before we even ask the question about what are the fundamental particles made of. That's something, a next thought. So our way of thinking about the microscopic formulation of the world, I mean, even this holographic idea we talked about, is not about space and time. So even in this holographic description, say, of part of space where we put the information on the boundary, we're not talking about the strings. I mean, that's something that should appear in the space as excitations of certain objects. So the starting point may be a different one than we have used earlier on in string theory. But a string theory will eventually be embedded or incorporated in this whole way we're gonna think about quantum gravity.